And so today's talk is counting on Poisson Regression with Scikit-learn. I'm a senior software engineer at Quantsci Labs, and I'm also a maintainer for the Scikit-learn project, which is a machine learning library written for Python. All the materials for this talk is available on GitHub, so let's begin. So this talk revolves around how to configure Scikit-learn for Poisson regression, and we'll cover many different models that could do this in Scikit-learn. And I'm going to throw in little fun facts about Scikit-learn throughout the talk, so hopefully there's something interesting for everyone. So now, when can you use Poisson regression? Well, there's many different use cases. For example, you have in agriculture, you could predict the number of rainfall events per year, so the counts. In another field, let's say risk modeling and insurance, you could model the claims, the number of claims as with Poisson regression, so it's another count. In predictive maintenance, you could model the number of interruptions per week. And that's something also you could model with Poisson regression. So there's a theme here. It's counting. And that's what is the traditionally used, the target data you use to do for Poisson regression. So there's many different models that do this in Scikit-learn. We're going to cover 3 of them. There's the linear model, the Poisson Regressor. There's the random forest with the Poisson criterion. And there's also the HistGradientBoosting, which uses the Poisson laws. So we're going to cover all 3 of these, and we're going to talk about how Poisson influences these algorithms at a high level, because there's not enough time to cover each one of these in depth. So it's nice to have a concrete data set to look at while doing machine learning. So I'm going to focus on this bike sharing data set. It's where the target is the number of bike shares for each hour. And this is a data set with 2 years of data, and it looks something like this. It has the count, which is the target. It has categorical features like the weather code, its holiday, its weekend, the season, and also some continuous features such as the temperature, the humidity, and the wind speed. So this is a heterogeneous data set. So there's a mixture of categories and continuous features. So you can see here that I have a column transformer. This is Scikit-learn's transformer that lets you deal with heterogeneous data. You can see that I have a one-hot encoder for the 4 categories. I set the remainder to be min-max scalar, which is going to be the temperature, the humidity, and the wind speed. So these are our continuous features. And there's something new here, like relatively new, the spline transformer for the hour feature. This is very useful for periodic features such as the hour, because hours in our data set goes from 0 to 23 and then back to 0. So in this case, I use spline transformer with the periodic extrapolation. And this is a topic in on itself, but the idea is that periodic spline features allows you to encode the periodicity of your feature. And there's a very lovely example in the Scikit-learn examples, a link at the bottom of the slide. But this is one good way to encode periodic features. All right, so that's how we're going to pre-process the data. I'm going to only use this for the linear models. The tree-based models doesn't need the pre-processing we talked about. So let's look at the linear model. We have the Poisson Regressor. It's the linear model. It's a part of a family of models, which are called the generalized linear models, or GOMs for short. General linear models have a linear piece, and this slide is the x times w, which is the data times the weights. And it has the target, which is the y hat, and then it has a function that links them together. And this h is called the inverse link function. Now, this problem becomes a minimization problem, where you're summing over some distance deviance between y true and the y predicted. And this deviance depends on the family distribution you're targeting. And in Scikit-learn, we also have L2 regression by default. Now, like I said, the deviance depends on the distribution you're targeted. So for traditional models like ridge, it's targeting the normal distribution, so the target domain is from negative infinity to infinity, and deviance becomes its normal square laws. But in our case, where we have Poisson, our target domain is from 0 to infinity. There's no such things as negative counts. So the domain is from 0 to infinity, and we have a different unit deviance. So it's a different optimization problem for Poisson. We also have other regressions like gamma regressor. And I'm not going to talk about it here, but it's available in Scikit-learn in our generalized models. So you can have a gamma distribution as well. Now, now the minimization problem, like this is this formula. The way we solve it internally is that we use SciPy minimize with LBFGS. So that's our only solver we have now, but where I'm looking forward to, there's going to be new solvers that are currently being worked on with the Shanovsky-based Newton solver and the Newton LSMR solver. Ongoing development, new solvers. So this is the GOM space is evolving in Scikit-learn. And notice that it's a minimization problem with an alpha, and the alpha is non-zero. Alpha is 1 by default in Scikit-learn, because Scikit-learn is a framework for predictive models. And from predictive models, regularization is helpful, because in your data sets, usually you have multi-collinearity, and regularization helps with this. So this is on by default, very similar to how logistic regression also has a regulation on by default. So that's the theory. In the code, the way we construct this thing is we have a pipeline with the preprocessor we discussed before, with the splines and the one-hot encoder and the min-max scaler, and then we create a pipeline with that preprocessor and the PoissonRegressor. We get like a pipeline that looks like this on the slide. And we're going to compare this to ridge, which optimizes for the mean square error. Now, we also need to evaluate this model somehow. So the data set we have is it's ordered, and so we have to split this data in such a way that we're training in the past and predicting on future data. So we also take advantage of time series split with 50 splits here. So I'm going to do this 50 times, and with max train size and a certain test size. These are all in hours, so I'm predicting 2 weeks out. This is how I'm going to evaluate, and I'm going to use 50 splits. So this is what the results are for the linear models. We have, I use the root mean square error and also mean Poisson deviance. The thing to note is, and the ridge is on top and the Poisson is on the bottom. This is, there's 50 little dots there. There's a swarm plot and a box plot on top of it. And you can see that the Poisson does better, the distribution of scores does better for mean Poisson deviance, so it shifts to the left, smaller is better. And also to note that Poisson also does better for the root mean square error, even though it's not something it's directly optimizing for. So the Poisson in this case better represents the data. Another way to look at this is using the distributions. And here we have the predicted distributions of our linear models. In this case, I found the predictions of the test beds that we saw before and then made a histogram. So on the left-hand side, that's the data itself. And you can see that's distributed like so. And there's in the middle, there's ridge, which is the predictions from the ridge model. And on the right, there's Poisson. You can see that ridge doesn't actually reproduce the target distribution. It's very normal-like. And Poisson better represents it. one thing to note here is that the leftmost bin is not a 0th bin. It's just really small numbers. So this data set is not zero-inflated. It turns out that in 2 a.m., people are still riding bikes. It's a non-zero number. So people still are riding bikes in the dead of the night. So that's one way to evaluate models. I'm going to show another way. We have calibration for regression. So this is very similar to from calibration for classification. And I'm going to show you the computation to get this calibration for a regression sense. So here we have y hat, which is the predicted values, y, which is the true values. And the first thing you do is sort the data in terms of y hat. And then, in this case, I'm going to bin the data with 3 bins, and I'm going to take the mean of each bin. So there's 3 bins, take the mean of the predicted values, take the mean of the true values, and I'm going to take a difference. And I can plot it with Matplotlib. All right, so you can see that, what does this visualization tell you? Well, the 0th bin has a positive difference. That means I'm predicting too many counts in that 0th bin. If you look at the rightmost bin, you can see that's negative, which means that I'm under-predicting the number of counts in that bin. And the goal is you want that plot to be close to 0. That means you don't have any difference between them. So that's like a very high-level overview of the calibration for regression. I can make these plots for our linear models, and this is what it looks like. We have range, which, so you can see that percent, the curve is closer to the 0. Also, you note that for ridge, the leftmost bin is very negative because it has negative values. It's going to underpredict. And also that in the rightmost bin, you can see that both models are underpredicting. And we'll come back to that when we look at the other models as well. So that's linear models. The next model we're going to talk about is random forests. Scikit-learn has random forests, and the way you configure this for Poisson is you set the criterion equal to Poisson. And how does this influence the algorithm? Well, random forests, you build many trees. And using Poisson influences how how the nodes are evaluated when you find the best feature and the best threshold while building the tree. So that's basically it. That's how it influences the algorithm. There's more details in the user guide and a link on the bottom right. And random forests builds many trees. It does bootstrapping, which is sampling with replacement. And it builds many trees with sampling replacement. Fun fact here is this uses multi-threading for parallelism. And because the tree building code mostly releases the GIL, and releasing the GIL allows this to run in parallel with multi-threading. So, fun fact. So that's random forest and how Poisson influences the algorithm. Now, if we look at the results here, you can see that the distributions for Poisson, for the Poisson ones on the bottom again, and the mean square errors on the top. You can see that the forest with Poisson also has the distribution shift to the left, but less so from the linear models because the random forest has more capacity. You could just learn more about your data. And this is evident when we look at the distributions. You can see the distributions. The middle one is mean square error, and the rightmost one is Poisson. And you can see that even for the mean square error, the distribution does look like the data. It's much better than what Ridge did. So in this case, the forest with default parameters still performs fairly well. But in another way to look at it, remember, it was the calibration. And so we also make the calibration plot for random forests, and you can see that they both do fairly well. Poisson is still, you could say it's closer to 0, but one thing to note is that the rightmost bin also underpredicts. So that means like for the largest counts, both these models under-predict the number of counts in our data sets. So I'll get into that after this as well, when we talk about the next model, which is the histogram-based gradient-boosted trees, which is Scikit-learn's implementation of the light-year beam algorithm. So the way this is enabled in Scikit-learn is using the loss equal to Poisson. So this is all you have to do. You set the HistGradientBoostingRegressor, set the loss to Poisson, and this enables it for the algorithm. I'm going to go give the TLDR and how this influences the algorithm. There's many different pieces to this algorithm. So for HistGradientBoostingRegressor is an iterative algorithm. The trees built are built in an iterative fashion where at each iteration it depends on the step before. So this is very natural to define this recursively. So initial condition is a constant. The constant is the maximum likelihood of your loss. So if for Poisson loss, that is the mean. Next, you do iterations. So T is the iteration number. F hats are the functions. And in this case, I'm adding a H hat, which improves on the predictions of the previous iteration with a learning rate. So how this works, well, the H hat depends on the gradients and Hessians, and these H hats are also trees. This is a very high-level overview. There's more and more details to this, but this is the overall idea. So, and the gradient Hessians is the gradient Hessians of the loss function, which is in this case Poisson. So while building trees, there's this concept of gain, which depends on the gradients and Hessians, and then while it's finding the best feature and threshold, it tries to maximize this gain. And remember, the gradient Hessians is for the Poisson loss. There's many parts of this algorithm, like in Scikit-learn, we use Python for parallelizing this with OpenMP. And there's like histograms, and there's many details to this algorithm. I recommend looking at SciPy 2019 about this talk about HistGradientBoosting by Nicholas, and which goes through these details. Now, there's one more last detail I didn't put here. It has to do with how the formulation from before doesn't restrict the domain from negative infinity to infinity. It restricts the domain from 0 to infinity. It can output any of your values. So the last thing about HistGradientBoosting is that there's also a function linking between the f hats we have to the predicted target, because we want to restrict the domain from 0 to infinity. So there's also an inverse link function, and for Poisson, it's the exponential. And this looks eerily similar to GOMs, because I see them very similar. So you can see that inside GOMs, there's x times w to be your term that outputs values of your numbers, while for gradient boosting, you have f hat of t, which is a summation of trees that does this. So it's connected. So that's the theory in a few minutes. Now for the results, HistGradientBoosting even has more capacity. So even for both cases, you can see that it does very well, even if you switch it to Poisson. You can also note that on the right-hand side, there's outliers in this data set, which means like for some splits, it does very bad. And if I zoom in, you can see that the distribution is shifted a little bit to the left. So that's the results. Next, distributions. You can see that HistGradientBoosting does recreate the distribution of the data. A thing to note is that for the middle case, with the mean square error, you can see that there's a bin to the far left. It still predicts negative. In this case, it does predict some negative values, which doesn't make sense for Poisson, for counts. But while the Poisson one doesn't. So it has that natural, it's more natural to use Poisson when you deal with count data. Now, for the lastly, we have the calibration. In this case, you can see that Poisson is more towards the 0. And you also see that same behavior I keep pointing out, where for the rightmost spin, it's underpredicting. The same idea. For large values, it's underpredicting. And this is one way to visualize it. Another way to visualize this phenomenon is to plot the predictions. This is a time series. And this behavior happens quite frequently in this data set, where the data, which is in circles and gray in the highlighted section, just peaks, and none of the models, which is the other 3 lines, the Poisson, the forest, and the histogram with % loss, can capture this behavior. So this usually means that there's something we're missing in the data that could capture this behavior that's not in the data right now. So that's another way to look at the final bin that has underpredicting in our data set, with our models. Okay, so that's Poisson regression with bike data. We went through these linear model, random forest, and HistGradientBoosting. There is 2 more topics I want to cover really quickly in the last 3 to 4 minutes. And these are commonly spoke about when talk about Poisson regression, and that's first is zero-inflated Poisson regression. And in our case, it's not zero-inflated, so we didn't have to think about this, but this happens. And traditionally, there's 2 ways to deal with this. It's a mixture model, where you model the likelihood of 0 directly, or you have a classifier that classifies the 0, and then a regressor that does the rest. And there's this really nice library called Scikit-learn that does the classifier and regressor case. So it has a meta estimator called Zero-Inflated Regressor that you can specify a classifier to classify the 0, and then a regressor that does everything else. So that's what we have to model zero-inflated Poisson regression. Another popular thing that appears when talking about Poisson regression is exposure. It's better explained with an example. In this case, this data set is insurance, car insurance. And each line is, we have the number of claims, and also the exposure, which is how long this insurance policy is existed. And in this case, we want to model the number of claims per year. In this case, the exposure is year. And we also have data about the vehicle and the driver. So the way this is modeled in Scikit-learn, you could take the division to get the frequency, and you could set the sample weights to equal to exposure. The idea behind this is that claims that's been around longer has more chance of getting a claim. The claims that have been around for 10 years are more likely to file a claim than policies that's been around for 1 year. So this is one way to think about this. And I would recommend looking at the example on the bottom that gives you more details about this approach. So we went through quite a bit, counting on Poisson regression with Scikit-learn. We went through the linear models for PoissonRegressor, random forest with the Poisson criterion, and HistGradientBoosting with the Poisson loss. All the materials here are available on GitHub or on this link. And I hope everyone here could take advantage of these features in Scikit-learn and for your data and modeling purposes. Thank you for your time and listening to this talk.
Thank you so much for a great talk. Just a quick reminder to everyone, if you have any questions, please use the Slack channel. And for this track, we're using track questions-slotnick-ballroom. And we do have one big question, and it's from Bin Zhou. Why does ridge regression and similarly random forest and gradient boosting tree underperform in terms of mean squared error comparing to Poisson regression, although the former one optimizes for the mean squared error?
Okay, if I understood that question, it's hard to hear, I think, right now. I think the question was, why does ridge regression underperform the mean square error? all the other ones optimized for. All right, so. So my sense is, practically it does, but the idea is because using Poisson represents the data more. Even if it doesn't optimize Poisson directly, it still better represents the data, and so the mean square error is another way. It better represents them more, so it does it better. It's very. That's my quick answer. I could. Here, I think you need this, right? Can you stand like there so I can hear?
It looks like there's one more question incoming. We can wait for a couple seconds. Andreas said, could be that the regularization is picked differently because of cross-validation?
Yes, I didn't fine-tune alpha at all. I left it on, it was left at 1.0 to make this simpler.
Next question from Pranay Charvdar. Is there any calibration method available in Scikit-learn for the underrepresentation for the higher values, like Platt's method or isotonic regression available for classification?
No. Yeah. It'd be interesting to see if there's. I haven't seen that applied in this context before. But.
This might be a good plug for we're having sprints this weekend, and so if you're interested in contributing, that might be a good time to join in the fun. Thank you so much. Thank you.